So before we talk about the convections, convection process, and we say that, do you remember this slide? We say that in the low opacity fluid, so the process will be a little different. So in low opacity regimes or systems, so the cool down point will reach after a longer period than the systems with the high opacity. Then we talk back to the Hertzsprung-Russell diagrams, and if you remember, we talked about the subjoint phase. This is a very transitive phase, and it's happened when the stars from main sequence 1 or 2 turns to the red giants. So these transited regimes, these guys make the island like that, and this island is mainly composed by the very short time lifetime. So we talk about it, and then we introduced the Hayashi. I think we introduced it also. I don't know that we talk about this Hayashi. I think we talk about instability and those. So today we are going to discuss about the red giant phase. So when the star turns finally from the main sequence to the red giant, so the phase which is called red giant phase, and this is actually happen when an object in the main sequence drop to the subgiant regime when it reached the Hayashi limit. Hayashi limits actually show that the convection zone depends substantially. So, and that's possible the star to be considered like a media with the highest chance for the convection. So how we can calculate the convective energy transfer? So before the study the convections, we have to talk about a little bit about the stars and about why the convections setup is happening as a subgiant cooling down process. Consider a gas. We consider a vessel of the gas in the star, which will move to the top if the density of that is less than the density of the surrounding region. So you have a vessel of the gas, so like a star, for example. And this vessel of the gas around the star, for example, is floating or bouncing with the space. So as long as the density is lower than the density of the environment, so then it will be undergoes to the convection relations, and it will go up. And if a vessel of the gas in the star fall down due to gravity, it's because of the density of that is more than the density of environment. So you have a good sense about that. So floating, the floating on the water, that exactly. So it happens when the density is lower than the density of the water, and the things will fall down into the water, for example, if the density is greater than that. So the ice, for example, is floating or bouncing over the water because the density of the ice is less than the density of the water, and it goes also top. So to make a quantify that, we back to the ideal gas equation. So this is the ideal gas equations. We write that in terms of the average of the mass. So what we will do is that in the star evolutions, all the quantity like density, pressure, temperature, and even the average mass, they are big numbers actually. So the aim of this calculation is that we want to find the equations for the change of the pressure versus the change of density and temperature. So we have to maybe write something here. Okay. All right. As usual, if you have a question, please turn on your microphone, because I cannot read it at the same time. So the equations which we have for the gas is ideal gas equation. This equation. So equation is rho. Rho is the density of a star, is the average mass over the K is the Boltzmann constant. You have a pressure here, and you have a temperature here. Okay. So what I want to find is that I want to see that when the density change a little bit, and when the pressure change a little bit, so how they are related to the change in the temperature. So we want to find delta P, for example, in terms of delta rho and delta T. So the strategy is that we always take a logarithm from these expressions. So if you take a logarithm of that, so it will be logarithm, I mean the Neperian logarithm, ln this quantity over K plus ln pressure minus ln T. T is the temperature. So what we do here, we have to take a derivative of this expression, but derivative with respect to the pressures. If you want to take a derivative with respect to the pressures, or just taking the derivative of this, I mean taking the differential of these expressions, differential of the logarithm of any functions, f, for example, is daf over f, as you know. So is daf, this is from the calculus, you know, daf. This is called a logarithm differential. Why we do that? Because I told you they are big numbers. So talking about the little change means that talking about the relative change, actually. The differential over the initial quantity is very important. Anybody remember such calculation before? You had such calculation before in physics 1 or physics 2 lab. You remember? In physics 2 lab, to calculate the error, you do this. If you take a derivative, so you will end with the equation d rho over rho. So d rho over rho is the logarithmic differential of the ln rho, and then you have a differential of p here. This is over the p minus a differential of t over t. All right, so you are talking about the little change. I mean, this is a layer. Look, this is a layer, and the temperature here in this layer of the gas of star is T. So here the layer will change temperature. Temperature change a little bit more. What you understand is that if density here is rho, so here density will increase it. So if the pressure here is P, so the pressure here will be P prime, which the P prime is given by the P plus delta P. P plus, what is the delta P? Delta P comes from here. This is the delta P, look. This is differential of P, but you can simply turn the differential to the real one. So it will be P plus delta P. So it will be P plus, look how I can find delta P. I just need one more P. here, and then I have to keep it turns all, move all to the one side of the expressions. Okay, this is wrong. So what does the equation tell you? That this equation will tell you the change of the row where the changes happened because of the change in temperature and pressures. All right, let's back to our slide. So you can see that if you want to talk about the rapidly change of the pressure, so you can talk about that when the change in temperature would be increased like P plus delta P. There is also a case that which this vessel of the gas actually will expand or is the conduct adiabatically. What is the adiabatically? Adiabatic means that there is no any extraction or input of the energy to do this process. Is like a process is fully happen without any contact with the environment. This is the vessel of the gas, as I told you, and this vessel of the gas is full of the molecules of the gas, and this is the environment. Environment. So as long as it goes up, so it means that if I consider rho from here, rho pre, and rho of the gas here, as long as the rho is less than rho prime, it goes up. And as long as it goes down, because rho will be greater than the rho prime, and you can see that. What does it mean rho less than rho prime? Means that rho prime can be, for example, rho plus delta rho. And this delta rho, from where you can get this? From the calculation of the logarithm of the previous slide. From here you can find delta rho, okay? And it is really depends that this delta rho is really very strictly depends to the rho, as you see, depends to the pressure, depends to the T, and depends to the differential of that. I mean, a little bit, not significantly, even little bit change of the temperature and the pressure make for you a change in the rho. So this is the delta rho is a function of that, and this functional form come from this slide, as you see. All right. So if it is the situations that the gas doesn't have any interactions, if this process, for example, be forbidden, energy never transfer to inside, or energy never go outside also, if this is the process. This is, we call it isolations. So isolation. So isolations, so is a process when there is no extractions or entering of the energy to the system. There is a parameter, we call it degree of we call it the index of the isolations, or adiabatic index. So for adiabatic index, we can show that if something happened adiabatically, so then the pressure in the physics 1, chapter 20, you have this. You can show that this is the conditions for adiabatic expansions of the gas. And if you talk about the density, so you can easily show that the P for adiabatic expansion will be proportional to the rho power gamma. What is this gamma? This gamma depends very strictly depends to the degree of the freedom of the gas. I mean, how the molecule of the gas can move. This is, we call it degree of freedoms. For example, if the molecule of gas just translations, so you have a 3 direction of translations, yeah? just moving, either in the x directions or y direction or z directions. Degree of freedom we can sometimes show by S or F. So in this case, S is 3. Some molecules, they just have a translational, but many of them have rotational. But you have sometimes the molecules which is rotating around one of these axes. If you're a chemistry student, you know that better than me. So you have a translation plus 1. So this system can have 3 plus 1 degree of freedom. Can you give me an example of the molecules which can have a degree of freedom of rotations? H2O. Or CO2 also. CO2 is a good example. H2O maybe has not enough rotations. CO2. So C can sit here, and those molecules will be O, and these molecules, it has a rotational, actually, a degree of freedom. But if the molecules saturated any type of the degree of freedom, if the number of degree of freedom increases up to any levels, then the adiabatic freedom coefficients, you know, it was 1 plus S over 2 over S over 2. So you see that the gamma will be 2 over S plus 1. And if S is infinity, so gamma will tend to the 1. And you will reach the equation of the ideal gas. H2CO2 also, yeah, this is very complicated what you say, yes, correct. But yeah, CO2 is, I think, it has a rotation also. You're right, safe. Thank you. This is a slide about degree of freedom. This is what I say, explain what I say. Translation is just moving. Rotations is, as you see, rotating. And there is a combinational case. Even there is a degree of freedom of vibrations. I mean, the molecules here looks like you have two balls, and this ball are connected with the spring to each other. Looks like that. And this is a vibrational, actually. So you have a frequency for this. So frequency for these molecules, you can show that it looks like a mass spring system. I can express this frequency for you in terms of the potential between these, but I don't want to do that. So this, you can express the frequency in terms of the potential. Clear. All right. If you back to the equations which I tell you that for adiabatic situations, P will be given as a polytropic, actually, or power law function of the rho. If you substitute this in the expression for and in adiabatic case, you know, because there is no transfer of the energy, so delta T remain the same, yeah, because 0, because energy, you know, energy is proportional to the T, yes, for the ideal gas. So then if there is no energy, if there is no difference of energy between the inside of the system and environment, immediately you can conclude that delta T will be 0. So if you substitute the P, as I mentioned here, this in the expressions, then you can see that the delta P will be proportional to the delta rho as following. If there is a possibility for convections, then the density should be less than the density of the environment. I mean, then the situations for the density will be changed. I mean, so you can write the equation which guarantee for you the case that the convection will happen. This equation which you will see here, which is given by combining the equations, the logarithmic derivative of the equation for the ideal gas and the equation for convections, it gives you the conditions for the packet of the gas of the vessel of the star to go up. And there are a regime of the temperature that if this, it will happen only if the temperature satisfies this kind of the conditions, as you can see. After all, if we combine all the informations, we can say that the conditions for the convections of the gas of the star is the one which is given here. Differential of logarithmic t over differential of logarithmic p should be greater than that, and this is the gamma. Actually, notice to derive this equation, it is little tricky. So you can read it from the book, and I show you this slide, but you see I didn't stand from them because it's a bit hard. So if I ask you that, I will ask something about this in the homework. Definitely not in the exam. It's a little difficult. And the chapter will be end here. There is a little left 2 slide. I will ask you to just read it, those 2 pages, to give you some estimations about the time which and then the star will be passed to the red giants, and some general information about that. So we end up here with this. So I just I wanted to just drop the slide to the folder for you you'll be able to follow this if you want. Just as I told you, the slide is exactly the same as the textbook, so we don't have more different. We don't have any difference between the what is written here and so here we are going to talk about the hoax. So